So today we want to talk about linear forms. So here's going to be our definition. A linear form on some vector space V over some field F is just a linear transformation that maps V, so I should give some names. So let me call it little f, that maps your vector space onto your field. So we've been thinking about linear transformations as being maps from one vector space to another vector space. But F itself is a vector space, right? It's not a very interesting vector space, but these are both vector spaces over the same field F. And so this is a special kind of linear transformation, one that just returns scalar values. And so let's try and give ourselves a number of examples to help clarify our thinking about this. And our first example is going to be somewhat of the canonical example. We're going to come back and see really this example has a lot going for it. But let's think, if you have vectors, say, in some space like Rn, or just keep it simple, let's say we're in R3, and I want to map them to real values, well, what can I do? Lots of ways we can turn a vector into real values. We might just add up the numbers. There's lots of things we could consider doing. But what is, I don't know, what's something you learn about in linear algebra, where you turn vectors into scalars? Okay, the norm is one way. That's a good idea. You could ask, what is the length of vector? What's another really important operation you talk about linear algebra? Dot product. Now the problem here, though, is I just have one vector I'm beginning with. I'm beginning with one vector. So I have some vector, let's say W. And I want to send that to some number. And so what am I going to do? Well, for my function, I'm just going to pick some arbitrary value V and just say that f of W is V dot W, right? For some fixed V in R3. So maybe I should give an example for this example, right? And sometimes to indicate this f is based upon some fixed v, I'll put a little subscript here, f sub v, right? So let's do a sub example. Suppose I fix, fix my v to be, well, let's just say 1, 1, 1. Then what would f of some vector w be? Let's say the vector w is the vector that has values w1, w2, and w3. What would that give you? F eating this vector w1, w2, w3, what's going to spit out? Yeah, just the dot product of 1, 1, 1 with w1, w2, w3. And the way we calculate, I didn't draw my dot. The dot product, so you just do 1 times w1, 1 times w2, 1 times w3, and you just get w1 plus w2 plus w3. So in fact, as a sub-example, we can think of the function that just adds up the values of the vector. But there were lots of other examples you could have, right? You could have made v be the guy that's just 1, 0, 0. What would that map then do? It would just recover the first value of your vector, right? Or you can make v to be, whatever you want. 1, 2, 3. One copy of the first value plus 2 copies of the next plus 3 copies of the next. So within this example, there are lots and lots of sub-examples that we could talk about. But let's actually check that this is in fact what it claims to be. So what does it need to be a linear form? It needs to be a map from a vector space to the real numbers. Check. But we also want it to be a linear transformation, right? So let's take a second to think, like, is this thing actually a linear transformation? So recall, to check if something is a linear transformation, we have two conditions that we're trying to check. The first is that, well, maybe you tell me, like, what does it mean for this to be a linear transformation? No, you're thinking of a basis. What? Yeah, so f of, well, see, now I'm getting confused because I have v's and w's down here, and I don't want you to, let's just call it x and y. F of x plus y should just be f of x plus f of y, where x and y are values in your vector space. X and y are vectors in V. And then also, so it's closed into addition, or that is the transformation respects addition. And then the second one is the transformation should respect scaling. So f of some scalar times x should be f of that scalar times f of x, where c is a scalar in f. And that's why it's important that V is a vector space over f, so we can talk about what c times x really means. Okay, so that's what it means to be a linear transformation. Yeah? Oh, sorry, we have a little bit of audio. Good? Better? Yeah. I should mention, sometimes it's a pain to check two things. Would it be nice if we only had to check one thing? Well, you could collapse these into one condition. So what is that one condition? Well, do you see it?
C into the first.
Just throw c in. Instead, you just need to check that f of c times x plus y is c times f of x plus f of y. Right, that's really all you need to check to see if something's a linear transformation. Why? Well, let c equal 1 and you recover the first condition, or let y equals 0 and you recover the second condition. So if you sometimes saves your time just by doing a single condition. Let's do that here. So let's say I have f of, so here I'm going to check this is linear. So here I'm going to check that really is a linear transformation. And so I'm going to consider what happens if I have f of, for some place, let's just stick with x and y, of c times x plus y, where x and y are vectors in R3, and c is some real valued scalar. Well, by definition, this is just going to be whatever your vector v is, dot this vector cx plus y. And then this will immediately follow from the fact that your dot product is, well, linear, but the way you probably learned about it in your first course linear algebra is that dot product is distributive. That is, this is just v dot the first value, cx, plus v dot y. And you learn that if you scale one value of your dot product, that's the same thing as pulling the scalar out. Why? Well, you can just think about if you multiply all the values of x by some number, and then you're timesing it by this other number v, and then you're adding it by the distributive property of addition, you can pull out that c. So this is the same thing as just c times v dot x plus v dot w. We're really just unpacking the definition, but then that is exactly c of f of x plus f of y. Okay, so it's linear. So that's one example of a linear transformations. That's a whole lot of examples, right? Based on whatever vector you make it, you have a whole lot of examples packed into this. Let's try and think about something like totally different. So instead of thinking of R3 or Rn, let's go to some other vector space. So I don't know, you guys give me a vector space. What's your favorite vector space you want to think about? Which one? E4. E4? P4. Okay, if that's what you want. Can I do P3? You want P4? P4 is a little bit big, and so when we do examples, it make it a little more complicated. Okay, I'm gonna run out of chalk. So we're doing a map from P3 to, well, we have to think what vector field, what is our ground field, where our scale is coming from. And so typically we're just thinking of this over the reals. You could do over the complex numbers, but let's just keep with it being over the reals. And so we want some map F that's going to eat some polynomial of degree up to 3 and spit out a real number. So how can you turn a polynomial into a real number? Like what might do that?
Integrate from 0 to 1.
Ooh, an integration one. Well, this is really nice. So your proposal is that we should define, so this is a map given by f of some function inside of P3, so let me call that g of x. So g of x is my guy living in P3. G of x lives here in P3. That this is going to give me out the number I get when I integrate from 0 to 1 my function g of x. It's like, well, is this well defined? Well, these are polynomials, so they're differentiable everywhere, they're continuous everywhere, they're integrable, so yeah, sure, like that's well defined, so good. We can solve this. Okay. So example, like a sub-example to this example would be something like f of the polynomial, I don't know, 1 plus x cubed should return what value? Well, the antiderivative of this is like x plus 1/4 x to the 4th from 0 to 1, which spits out 5/4. Yeah. Okay, so we understand how this works. It eats in some function, it spits out a real value. What do we need to check? Well, is it linear? Is it a linear transformation? So, is this a linear transformation? So we ask, what happens if I have f of, let's say we have some constant times g of x plus some h of x. So I start out with two functions, g of x and h of x. They're both in P3. By definition, that is just going to be my definite integral from 0 to 1 of c times g of x plus h of x dx. And now what can I do? Yeah, we're going to use the fact that integrals are linear. Well, you maybe didn't learn it with that language, but you learned that the integral of a function plus a function is the same as just the integral of that first function plus the integral of that second function, as long as both the functions have well-defined integrals from 0 to 1, from 0 to 1, which they do, because they're both just polynomials. And then you learn that when you have a c, you can pull it out, right? This is like week, 14 of calculus 1 or whatever it is. You're like, what is this? Well, this is just like increasing the height by some factor c, so it's just like scaling the area by a factor of c, so you can pull that c out, and you just have c times the area from 0 to 1 of g of x plus the area under h of x from 0 to 1. But then you're like, that is exactly just f, a c times f of g of x plus f of h of x. So like, sure enough, it's linear. Okay, so this is almost like, these definitions sometimes can become quite silly, but we're doing this just to remind ourselves like, oh, these kinds of things actually have the properties we want them to have in order for them to be linear, right? So lots of stuff you thought about before in your life, so secretly linear, maybe without you realizing it. Anything else you can do to turn a polynomial into a number? Integration was a good one. What else you could do? Like, let's say you're just a high school student. How do you turn polynomials into numbers? You want to find the zeros. Oh, we can think about finding the zeros of a polynomial. And like, is that a linear thing? I mean, first of all, it's like, that's not necessarily going to return a unique real value because you might have multiple zeros. So maybe you would say like, find the smallest zero or something, right? Is that linear? Okay, so like find a counterexample. You know, like find two polynomials that both have like zero somewhere, but then when you add them up, well, let's see, like I'll just show you a counterexample. You know, so your suggestion was like, you find the zeros of something. And I'm like, you know, what if you have one polynomial that, like, you pick it so like one is up here when one is down here. So those will add up and give you like a new zero, right? When they add up, they give you a zero. But that zero would be like very different than, you know, whatever zeros it had before. Or even just like, just take the constant polynomial here and like the constant polynomial here. Like, those have no zeros. So like, I don't even know what you mean by take the zeros because not every polynomial has a zero. So those have no zeros. But when you add them up, there's zero everywhere. So this is not really a comprehensible definition. Okay, so that's not going to work. We're not going to do anything with zeros. Not all polynomials have zeros. And that's just the first of many problems. Finding zeros doesn't respect this linear process. What else can you do to a polynomial to get a number? Plug in a value. So instead we could have defined f as some evaluation function. So maybe I'll just call it e for evaluation. And it's like, how do I turn a polynomial into you know, some guy? Or, well, all I have to do is I pick my favorite number, 3, and I send my polynomial g of x to the value e3 of g of x, which is just going to be plug 3 in. Plug 3 in. You don't have to do 3. You could do 2, or whatever number you want, right? Okay, so is this linear? Well, you know, at this point, it's kind of just routine to check. But sure enough, if you just think about this map, like what does E3 of CG plus H give us? And you'll just say, okay, well, this just means plug 3 into this guy. So this is going to be C, I suppose to be precise, we should think of it like this, where we should say it's this function with 3 plugged in. But that's the same as just plugging 3 into both guys, which then is the same as just recovering C times E3 of G of X plus E3 of H of X. So like, sure, that's like immediate that it's linear. Okay, I think we've seen enough examples. We could do more. Like if you want to do something on matrices, what might you do? What's a way to turn a matrix into a number? Determinant? Is determinant linear? No, we said determinant's not linear. We talked about that. Because what happens when you scale by some value c? You multiply all the columns by c, which is actually going to scale the determinant by a factor of c to the n, where n is the number of columns. So we don't want to say determinant. What else can you do to turn a matrix into a number? The trace. If you scale by a factor of c, what happens? You're just scaling the trace by c, distributive property, right? And if you add to matrices, you're just adding the trace. So determinant also doesn't play well with addition, right? The determinant of a matrix m plus a matrix n is not the determinant of m plus the determinant of n. So trace though, trace would be a good one. So, maybe it was listed as the last example. The trace map from, say, I don't know, 2 by 2 matrices over the real numbers to the real numbers is also a linear transformation. Is a linear transformation, and hence we call it a linear form. Okay. What I want to say, though, is that we've done lots of examples, but what I want to say is that in some sense, this first example of dot product is really the canonical example. That really, in some sense, all these other things are just dot products. And so that's going to be our theorem. I claim that really, this is all just like, in some form, a dot product. Now, this story is kind of familiar. When I first introduced linear transformations, we saw lots of examples of linear transformations, and I said, in some sense, they're all just secretly matrices, right? And so the same thing here, a linear form, lots of different examples, but in some sense, they're all just secretly some kind of dot product. So let's go ahead and state that. So again, I need to emphasize this is finite dimensional. So given a finite dimensional, in general, you don't need these to be finite dimensional, right? You could take the space of all polynomials or whatever, but then you have to be a little bit careful in thinking through some things. But for this theorem, we need to limit our attention to finite dimensional. If we have some finite dimensional V over some field F with some basis B, then given a linear form, which would be some map from V to the field that's linear, it's a linear transformation, we want to say there exists a unique, just like in the theorem of matrices, a unique vector V such that f of any vector in V, f of any vector W, is secretly, and here I'm just going to write this as my vector transpose times W. dB. So like, what do I mean by this? So like, let's be careful to think about how matrix multiplication works. So here, these are like guys in some finite dimensional guy. Let's say this is dimension n. So this is going to have n values when expressed on that basis. This is going to have n values. How can you multiply two matrices that both have n values? Well, if you make this a 1 by n and you make this an n by n, it'll spit out a number. It spits out a 1 by 1, which we can think of as being just an element of f. It's really a 1 by 1 matrix, but we're just going to treat it as an element of f. It's just canonical mapping. It's the same as just whatever the element of f in it is. And so that t is just to remind us that, while this is an n by 1, this needs to be a 1 by n, right? So while this is going to be something with, n by 1, n rows, 1 column, well, this is something with a lot of values like this. In order for the multiplication to work out, we need to line this one up like this, right? Because then when we do row by column, we'll get out a single value. Then it'll come out to be something that we can think of as living inside of f. Okay, so just note, if f is equal to r, which for us typically it is, this is the exact same thing as just the one vector dot the other vector. We define our dot product for real valued things. What if it's complex value? Well, I don't know if you talk about this in your first course of linear algebra. I imagine you must. With complex valued vectors, like a vector in Cn, you have to define your dot product a little bit differently, right? because you want to preserve the properties of it. So you do this like conjugate transpose instead of just the transpose. So you got to take the conjugate of the values in one of the guys. So just to ignore thinking about all of that, I'm just saying, if you're just dealing with real numbers, then this is just the dot product. But in general, it's just this thing, which is really just an exact, generalization of the dot product. So like, why is this true? So proof. Well, it follows immediately from our definition, a linear form is a linear transformation. So since f is a linear transformation, we have, from our previous theorem, that there will exist some matrix, there exists a unique matrix M that represents that linear transformation such that if you want to express, this should be this expressed in terms of your basis. If you want to express, no, this is just a real number. This is just a real number. We don't have to change that. Such that if you have f of w, it'll just be your matrix times w expressed in terms of your basis b. But then you just think about what that matrix has to be, and then you're like, that matrix has to be a 1 by n dimensional matrix. And so that matrix is really just a vector laying on its side. And so you're like, okay, whatever the values of the matrix are, that's where your v is. So this is an immediate corollary from the previous theorem we proved about the existence of matrix, but just in the simple case where one of your vector fields happens to be just f. So it's just one-dimensional. So your matrix has only one row to it, so it becomes just a vector laying on the side, some vector transpose. Or you can think of it as just two vectors dotted together is your operation. So I guess what we should do is go back here and figure out what is the secret vector that corresponds to some of these linear transformations. Like let's look at this one, right? I'm saying that there's some secret, I'm claiming, our theorem is telling us that there should exist, really like this blue, right? Can you see it okay? I don't know why I don't use it more often. This is beautiful. There exists some vector inside of P3 such that your E3 of any vector W is really just, these are over the real numbers, so we can think about in terms of dot product, is really just V dot W. And it's not really V dot W, because V and W are polynomials, but it's the corresponding vectors that correspond to V and W dotted together, where these are vectors that is reading off the coefficients with respect to some basis B. So let's just like pick our basis to be a nice one. Like let's do the kind of natural standard basis for P3. The basis that's just 1x, x squared, x cubed. Then we just have this coefficient, right? You're just reading off the coefficients of some polynomial and reading off the coefficients. And we're saying that evaluating by plugging in 3 is really just multiplying those coefficients by some other collection of coefficients. So like, let's think, like, is that really true? Like, is plugging in a number into a polynomial the same as secretly a dot product? Like, they seem like two very different ideas. But like, think about it. Suppose your W can, like how should we write it? Well, let's just say it has coefficients, maybe a plus bx plus cx squared plus dx cubed, right? We could write your polynomial polynomial W like that. Then, what is the evaluation linear form do to W? Like, what happens if you just plug 3 into your polynomial? What do you get? You're like, well, it's just one copy of A plus 3 copies of B plus 9 copies of C plus 27 copies of D. Do you see the dot product now? Like, this is what dotted with what? What is a vector V that we're dotting things with? 1, 3, 9, 27, dotted with your original guy, A, B, C, D. Right? It's the dot product of the coefficient vectors in terms of basis B. So for us, our vector V just came out to be the vector 1 plus 3x plus 9x squared plus 27x cubed. Okay, so I think that's quite nice. How about this one? You're like, surely like integration isn't secretly like a dot product, right? So let's try and think about integration. Let's use a new color. We use yellow. So I'm trying to find some vector, something inside of my P3. So some vector living inside of there. I guess I can call it V of x. This is kind of a funny name, but I'm trying to find this vector, right? So that I can think of this integration as secretly just being, whatever the coefficients of V of x are, dotted with the corresponding, so this is the coefficients of him in terms of my standard basis, times the coefficients of my gx in terms of my standard basis. So you're like, it's kind of a weird one. Well, again, let's just proceed by writing g of x. Let's just say g of x has some like standard form. We can write it as some a plus bx plus cx squared plus dx cubed. Then what is the antiderivative of this going to be? And then you plug it in the values 1 and 0. Like, what does this come out to be here? Well, its antiderivative is ax, and then you plug in your 1 and your 0. So that just becomes a. bx becomes 1/2 bx squared. So then when you plug in 1 and you subtract plugging in 0, you just get 1/2 b. Integrate like cx squared, you get 1/3 cx cubed. So you just end up with 1/3 of c. Plus, and it's like, okay, integrate dx cubed, you get 1/4 dx to the 4th. And then you plug in your bounds, you just get 1/4 d. 1/4 d. And now do you see it as a dot product? It's like, yeah, that is just 1, 1/2, 1/3, 1/4, dotted with A, B, C, D. A, B, C, D is the coefficient vector corresponding to the vector G, and 1, 1/2, 1/3, 1/4 is the coefficient vector corresponding to a V that would be just 1 plus 1/2 x plus 1/3 x squared plus 1/4 x cubed. Okay, so maybe this is enough examples to begin convincing you that secretly what's going on here is like some kind of dot product, right? This is cool. I think this is really cool, right? It's like secretly you weren't doing calculus and your whole life you've been doing linear algebra, you just didn't know it, right? Like all of math is just linear algebra. Okay, that's not true at all, but it's kinda true. So, let's just celebrate it nonetheless. Okay, so we've been talking about linear forms as being like individual maps, but what if you want to think about the collection of all linear forms? So this is a common thing we do in mathematics, where we'll introduce like some map F, we'll think about your properties of F, and it's like, well, now we understand it. F is just secretly acting like dot product, right? But now let's like think about all possible F, and think like, is there some structure to the set of all these things? So here's my definition of linear form. But like, let's think. Suppose I have two linear forms. Given some linear forms, say F and G, that are both linear forms from V to F, what can we do to those linear forms? In particular, can we make sense of adding those linear forms? What would I possibly mean by F plus G? Well, it's like, whatever this is, you can think if you eat some value in V, that's just, let me call this W still. If I eat some value W that's in your vector space, we can just define that to be just F of W plus G of W. Is that good? Because like the addition of two linear forms is just a new map that does whatever F does plus whatever G does. Okay. Is this new map linear? F was linear, G was linear. Will this new map be linear? Is F plus G a linear transformation? So like, well, you just check. You just do like F plus G of, I don't know, some number of copies of some vector X plus some number of copies of Y. And then that's just defined to be F of Cx plus Y plus G of Cx plus Y. But we started out with F and G as linear forms. And so therefore this is linear and this is linear. And hence that's just C times F of X plus F of Y plus C times G of X plus G of Y. And you're like, then what can you do? Well, here you have some F of Y plus some G of Y. So that's just some F of some F plus G of Y. And here I have like C F of X and C G of X. So I can put those next to each other, factor out the C. So it's C times F plus G of X. So this is C times F plus G of X. And it's like, sure enough, F plus G is linear. So you can add linear forms. What else can you do to linear forms? Want to take a wild guess? You can scale them. Just like we defined F plus G of W, we can define what C of F of W would be in just the most obvious way possible. It's just C times whatever F of W is. Right. And you can check that's still linear. That is, if you have linear forms, F and G, F plus G is linear, and C of F is linear. So they're also linear forms. Now we started out with two linear forms, and we got that you can add them or you can scale them, and it's still a linear form. So what would the set of all linear forms be? It's a vector space. I mean, there's more things to check. Like, is there a zero linear form? What would that linear form be? It just sends everything to zero. Yeah. If G just sends everything to zero, then this should be the same as just F of W, right? Because I was adding zero to it. And, you can check that all the properties of vector spaces are fulfilled. And so you actually can talk about a vector space of all linear forms. And so we're going to call this the dual space. So here's my definition. The dual space, I'll sometimes just call it the dual, of some vector space V over a field F is, I'll denote it V star, which is the vector space of linear forms. That are just maps from V to F. What's the ground field for this guy, V star? What's the ground field for the dual of V? Well, it should be the same, because here for the scalars to make sense, scaling is coming from F. So if your original vector space is over F, then your dual is also over the same ground field. So your ground field needs to stay the same. So this might seem quite mysterious to you, right? You're like, what kinds of creatures would live in here? But, you know, like, I think we've already kind of seen some examples, right? So here, if we think about like, say, all linear forms from R3 to R, we said that these are secretly all dot products, right? So each F corresponds with some vector V that's secretly some dot. And it works in such a way so that F of your starting vector is just V dot W. So the collection of all linear forms is just the collection of all vectors V. Or like they're isomorphic to each other. There's a natural isomorphism. That is, if you want to think about the relationship between R3 and R3 dual, is just there's a natural relationship between each vector and the map F that is performing dot product with that vector V. So there's a natural isomorphism between those. And it's not just happening, you know, with your vector space like R3, but by a theorem for any vector space. If you want to think about like what is the relationship between some vector space V and its dual, you're like, well, for any linear form F, there corresponds some vector V by our theorem right here. There exists a unique vector. And so there's a nice one-to-one correspondence between these. And so you get an isomorphism. But like, be careful. These are vectors. These are maps that are taking vectors to real numbers. But one of the immediate like corollaries of this is that if V is some nice finite dimensional thing, then your dimension of V is just going to be the same as the dimension of your dual space. Maybe in the last 2 minutes, I can just mention like there's no reason to stop here. We can also talk about the double dual. So if I have some vector space V, the double dual is just the dual of the dual. This is going to be the vector space of linear forms on V dual. Now this is going to get quite wild because it's like you have V, you have V dual, and you have V dual dual, the double dual. So it's like, what's going on here? Well, in here you have some guy F, which secretly is like dotting with some guy V. But let's try and think about like what's going on here in the double dual. So like what is something in the double dual? So let me try to like paint a really clear picture of what something in the double dual like even looks like. So let's say like phi is some element of V double dual. Then that means phi should be a map from V dual to whatever your ground field F is. So what this should do is this should take values like F and spit out a vector. So how is it going to do that? Well, I'm going to suggest if you just consider there's a natural, just like with the dual space, we can say that for every phi there exists some vector W, such that what ends up happening here is this can just act like, well, we can just define this to be F of W, which then F corresponds to some vector V, so this corresponds to some vector V, so then this is just V dot W. Now, this is quite strange, but you think what your F is doing is it's sending your W, whatever vector W you have, to V dot W. It corresponds with some vector V. But then what this phi is doing, phi sub W, is the one that sends F to, F is getting sent to phi of F is becoming F of W. Okay. This is getting very abstract at this point. What's the big takeaway? These are vectors. These are maps on vectors. These are maps on maps of vectors. But at every step, you have a natural isomorphism, and the dimension of all of them is the same. The dimension is all the same. These are all isomorphic vector spaces. Here, this map is based on your choice of basis B. Here your map's a little more independent. It's just plugging in whatever the W is. This map really just taking a vector W and saying this is the map that corresponds, this is going to correspond to some W. So you have some natural isomorphisms. We'll play around with these more in the future.